enough chatting about why so many things seem to be bell-shaped. Let's actually look at something that is bell-shaped and see how those features of its bell curve can help us solve problems. The first one I want to look at is pretty simple, and because it's pretty simple, it tends to get abused quite a bit. It's the idea of IQ, Intelligence Quotient. Now, the key word here is quotient. Most of us have heard of the idea of IQ, measuring someone's IQ. But a lot of folks are surprised to learn how it's actually done. So what you do is, you give somebody an IQ test, and I'm not going to get too much into that. Take a psychology class, I'm sure you'll talk about that a lot. And then you get a score on that IQ test. Now, the raw score you probably don't see. They probably just come back and tell you what your IQ is. But the score on that test is known as your mental age. And you take that mental age and you divide it by your actual chronological age. And that forms a ratio. Turning that ratio into a percentage by multiplying it by 100 gives you your IQ. So just for example, I'm 48. If I took an IQ test and it came back and it said I'm 24 mentally, I would take 24 divided by 48, get 0.5, which means I have a 50 IQ. That's what my IQ score would be. But if I came back and I got a 72 on the IQ test as a mental age, 72 divided by 48 is 1.5, I think if I did the math right, 1.5. So I'd have a 150 IQ. Now, I'm making those numbers up for purposes of illustration. We actually know, when I say we, folks that study IQ actually know quite a bit about the distribution of IQ scores in the general population. Here's one thing they know. Okay, so IQs are normally distributed. So what that means is, you've got IQs that we can plot on the horizontal of a graph, and the frequency of those IQs kind of is shaped like that. Okay, pretend that's a symmetric bell curve, equal on both sides, tailing off to the ends. We'll get better computer-generated ones later, but this will do for right now. Okay, now, what is where? Well, down here are going to be the IQ scores. That's what's going to be plotted down here on the horizontal. The lowest ones are over here, the highest ones are up there. What is low and what is high? Don't worry about that too much, although I've thought about it a little bit. I'm assuming, I guess the smallest IQ you could get is 0 if you tested on that IQ test and got a mental age of 0. Like, you test exactly as a newborn. I guess you can't have a negative IQ. Although I've met some folks that challenge that notion. So I'm guessing 0 would be the lowest. And as far as the highest goes, every once in a while you hear something about, this person has the highest IQ on record, and I think it's over 200, but it doesn't matter. The numbers will come in the next little bit. So the IQs are going to go here. Lower ones to higher ones. So earlier I said I made up two fictitious IQs of 50 and 150. All you got to know right now is 50's more to this side than 150 will be. Okay, what does the curve show us? And this is the interesting part about the math. The curve shows us the likelihood of a given IQ. So if someone's IQ is here, it means the percentage of that IQ in the population is up on the curve. If someone's IQ is here, it means the percentage of the IQ is in the curve. I know I didn't put any vertical axis here, and there's a reason for that. We'll come back to that as well. But hopefully you see that because it's bell-shaped, these are more prevalent IQs than these. And we'll get into what those are in a second. But just like anything else that's bell-shaped, the average has a higher prevalence than the tails. So that's what IQ being normally distributed kind of looks like. Let's get some more information. Okay, so now we know that the average IQ in the general population is 100. Now thinking about that logically, if I'm 48 and I test as a 48-year-old, that means I have an IQ of 100. Okay, I'll buy that. That kind of makes sense. So that means if I drop in a line right here, let's add some color. Let's make this pretty. that's my average. I'm going to call it mu. And the reason I'm going to call it mu, pretty simply, is because this is assumed to be a population measure. It's a parameter. So we can call it mu. And that mu is going to be 100. And you know what? I'm going to put the mu at the bottom and put the 100 at the top. So 100 is going to go up here. You can tell I really planned this well today. 100 is the average score. There we go. All right. Now, standard deviations. This is how much we can vary from side to side and what it implies about how many people are in that range. Standard deviation is 15 IQ points, which means we either have to go up or down 15. So I'm going to approximate this. Let's get some different colors in here. I'm going to put it out here about. Okay? So now that is going to be 15 up is 115, 15 down is 85. Symbolically, and I'm not sure how important the symbolism is, this is going to be mu plus sigma, and this is going to be mu minus sigma. You might remember that from a few weeks ago with standard deviation, because that's what that is the population standard deviation, little sigma. Okay, how about a second standard deviation? We can go out further. We can go out 15 more. If we go up 15 more up here, that's going to be 130. And if we go 15 more down here, that's going to be 70. And this is going to be 2 standard deviations down. And this is going to be 2 standard deviations up. Whoops, it's a terrible sigma. Okay, can you still see all that okay on the camera? I think you can, yeah. And you can go further. You can go as many standard deviations out as you want, and we'll get into that, I promise. But this, I think, does a pretty good job of capturing the big idea. The center is in the middle. It's symmetric on both sides. That tells us something important, doesn't it? That tells us that those with 115 IQ are just as prevalent in the population as those with 85. So those that are 1 standard deviation below average are just as prevalent as those that are 1 standard deviation above average. Now, I want to take a moment here and discuss something that I mentioned in the first part of this. I said we have to look at this graphically. Why? Well, this is the first time we're really going to be looking at data that's not purely discrete. And we're going to be looking at it in detail. Here's what I mean by that. If we start at an IQ of 100, what's the next biggest IQ up from 100? Think about that for a second. If you said 101, that's not entirely correct, is it? Because couldn't you have an IQ of 100.5? Or couldn't you have an IQ of 100.4? Or 100.2? Or 100.1? Or 100.01? Or 100.001? And there lies the problem. Therein lies the problem. This is why we have to look at this graphically. Because if we tried to make a t-table out of this, it would be infinite. You'd have too many. There's no next continuous number up from 100. With discrete numbers, sure. If you roll a die and you are keeping track of how many times you see 2, the least number of times is 0. The next biggest number of times is 1. There's no half a 2. But with a measurement like time, which is what this is based on, right? Mental and chronological time, those are continuous values, which means you can have lots of infinite decimals in them. So there really is no next number up from 100. So what you're going to notice, and this is going to sound familiar to you, is we're going to talk about ranges of values. Here's one that you've heard before. There. I just shaded 1 standard deviation around the mean for IQ. That means I just shaded the percentage of the entire graph that's between 85 and 115. IQ scores are between 85 and 115. And you know what that percentage is already. You know that that percentage is about 68%. You know that. You know that because we learned it, we counted it, we calculated it back in the day on discrete data. But what I'm here to tell you now is, if you run the math on this, and I'm going to run the math on this either in this set of videos or the next one, I'm going to show you the connection of the mathematics between what we did earlier and the way we deal with continuous data. It's a little bit tricky, and I'm going to give you a 30-second introduction right now. It involves filling up this range with lots and lots of little tiny rectangles. That's all I'm going to say for now. I'll have some videos you can watch later if you want. But I can accomplish that by simply shading the region. And you learned last time that that's 68%. More to come on where that 68% comes from in those videos I'm mentioning. There's also another range of values you remember from back in the day. If we start all the way out here at 70, and shade all the way to 130 and include all this blue stuff, that's 2 standard deviations. It's also not very clear on the video. I'm going to draw the hard lines here so you can actually see them. That's a little better. And you remember that's about 95%. That's about 95%. And we dealt with these percentages, like I said, a few weeks ago. We're going to deal with them more now. So let's see how some modern IQ classifications tie into this curve and these values on this curve.